So we've done a little bit with writing radicals in simplest form in the past, but we focused on doing so with square roots. So let's review how we would deal with simplifying radicals, writing them in simplest form, first when we're dealing with square roots. So the way we would do this normally is we would try to think of the biggest perfect square that we can think of that goes into 45. So that would be 9. That's the biggest perfect square that I can think of that goes into 45. And then I write down 9's partner. It goes in 5 times. All right, and the square root of 9 is 3, so that comes out of the square root, and the 5 stays behind. And that's it. That's simplifying the square root of 45. And then we can do the same thing with the square root of 48. The biggest perfect square I can think of that goes into 48 is 16, and it goes in 3 times. Now, you may not know your multiples of 16, so 16 may not have been the first thing that came to mind. So just always make sure that after you pull out a perfect square, that you double check that there isn't still a perfect square that you can pull out. So the square root of 16 is 4, and the square root of 3 is left behind. So always check that number that's left over under the radical. In this case, check the 3, and make sure there's not a perfect square that you can pull out of that. Alright, so now we're getting into bigger roots, bigger, higher radicals than the square root. In this case, this one is a cube root. So what we're looking for is the biggest cube root that we can think of that goes into 48. In this case, the biggest one I can think of is 8. That's a perfect cube. I know that because I can see it on my exponent chart. So the cube root of 8 is 2, and that can come out. And the cube root of 6 stays behind. And you just want to make sure that you write the little index number here so that it's still clear that it is a cube root and not just a square root. Alright, and let's do the same thing, but this time with the fourth root of 48. So we're looking for the biggest perfect fourth that goes into 48. I'm thinking 16. 16 is a perfect square and a perfect fourth. So the fourth root of 16 is 2. 2 to the fourth is 16. And I'm left with the fourth root of 3. And again, I double check. Is there anything I can pull out of that? No, there isn't. And we also learned how to do operations with radicals in our quadratics unit. We learned how to do it specifically with square roots. And when we would do that, we had to make sure that the radicand, that's the number under the radical, in this case the 3, we have to make sure that the radicands match and also that the index or the root matches. In this case, these are both perfect squares, so they match. So I'm basically working with 1 square root of 3 and I'm adding 4 more to it. So altogether I have 5 square roots of 3. You add the numbers in the front, but you don't do anything with the square roots. Let's look at this next one. We need the radicands to match. Right now they don't match. And we need the indexes to match. In this case, they do match. They're both square roots. But what I need to do to be able to add these is simplify one or both of them to try to get the radicands to match. So 3 root 2 is simplified all the way. I can't do anything else to simplify that. But the square root of 8, I can simplify that because I know that a perfect square goes into that, 4, and its partner is 2. So if I simplify that, 4 comes out, and 2 stays behind, and now my radicands do match. They are both square root of 2. So I've got 3 square roots of 2 minus 2 square roots of 2, which altogether is 1 square root of 2. And I don't really need to write that 1 in the front. It's kind of understood, so I can just say square root of 2. So what we were doing with square roots is the same thing that we have to do for other roots, for other radicals. So we always need to make sure that the radicands match. That's the number under the root, okay? They match in this case, and that the index matches. That's this 5 here. So the index matches, so I can simplify this. I've got 7 fifth root of 12 minus 1 fifth root of 12. So that gives me 6 fifth root of 12. And there is no perfect fifth that I can pull out of 12. So that's all the way simplified. All right, let's do the next one. I need to make sure that the radicands match. Right now they don't match, and I need to make sure that the indexes match. Otherwise I can't do anything with them. And they do match. They're both cube roots. So I need to try to simplify both of these. So, trying to simplify the cube root of 81, the biggest perfect cube I can think of that goes into 81 is 27, and it goes in 3 times. And the biggest perfect cube that goes into 24 that I can think of is 8, and that goes in 3 times. Okay, so we pull out these perfect cubes, 27 and 8. The cube root of 27 is 3, and the cube root of 3 stays behind. And the cube root of 8 is 2, and the cube root of 3 stays behind. Okay, so now I've got both my radicands and my indexes matching, so that means that I can combine these. I've got 3 cube roots of 2 minus 2 cube roots of 2. That gives me cube roots of 3. 1 cube root of 3, which I can just write simply as cube root of 3. So in our last unit, we also did multiplication and division with radicals, but specifically only with square roots. So whenever you are dealing with that, the deal is that the radicands, that's the number under the square root, they don't need to match. Just the indexes need to match. I need to have the same square root. So in this case, both of these numbers here, the square root of 6 and the square root of 2, they're both square roots, so I'm in good shape. I can combine those. So I need to basically combine the numbers outside of the radical, multiplying them together. So that's -7 times 1. There's an understood 1 here. And then combine the square root numbers together, put them under the same radical. So I end up with -7 root 12. And then I need to make sure, now that I've multiplied these, that I can't simplify this because my number under the square root is now a different number. And it turns out that I can simplify this. There is a perfect square that goes into 12. It's 4, and it goes in 3 times. So I can pull out the square root of 4, which is 2, and leave behind the square root of 3. So I end up with -14 root 3. So always double check what you get at the end under the square root and make sure that you can't pull anything out of it. All right, so let's do this next one. And I know it looks a little bit more daunting because it's cube roots, but we're going to do the same thing that we just did with the last one. So we're going to combine the numbers outside of the radicals. So 2 times 5, that's 10. And then I'm going to combine the numbers under the radical together in the same. I'm going to squish them together and put them under the same radical. So I've got 10 cube root of 12 times 18, which is 10. 10 stays on the outside. 10 cube root, and 12 times 18 is 216. And if you look at your exponent chart, you will see that the cube root of 216 is a whole number. It's 6. So 6 cubed is 216. So this is 10 times 6, which gives me 60. A nice, neat answer for what was originally a pretty messy looking problem. All right, let's look at the next one. This is something that we dealt with in the previous unit. Some of you may immediately try to rationalize it, and that's fine, and you will end up with the same answer at the end. But a quicker way to get there is put these together under the same square root, because just like you're allowed to split square roots up, you're also allowed to squish them together here. So the square root of 20 over 5, that just reduces to the square root of 4, and that's 2. Now, if you had tried to rationalize it first, it would have been a bit more work, but in the end, after you simplified and reduced, you would have still gotten 2. All right, this next one, I can do the same thing. Even though they're cube roots, I can still squish them together. So 18 over 9, well, that reduces to 2, and that is not a perfect cube, so I leave it like that. And that's okay to have that as an answer. As long as it's not in the denominator, I'm fine with that. Okay, and then this last one, we treat it the same way. We can try to put these together, see if it reduces. 96 over 3. Well, that does reduce. 96 divided by 3 is 32. And the fifth root of 32, this is one that you need to memorize, is 2.